Again after the lunch break and the lab also. So we had a bit of a deep dive in piezo-ceramic materials, and this lecture now, the second lecture of the day, is on polymer-based functional materials. As you might have noticed, I slightly changed the title. Originally it was Electroactive Polymers, and now I renamed it to Polymer-based functional materials. Why is that? I added also some slides on shape memory polymers, so we have electroactive polymers in it, and also a bit on shape memory polymers. As always, learning goals at first, or learning objectives. After the lecture, you should know different types of polymer-based functional materials, and also should be able to identify their advantages and disadvantages, also in comparison with the piezo-ceramic materials. Then, after the lecture, you can explain what causes the piezoelectric effect of PVDF, so a polymeric material also having the piezoelectric effect and how it is utilized. Then you should be able to describe the difference between electric and ionic EAPs, electroactive polymers, and you can describe the principle of shape memory polymers, but this we will only visit very briefly. So we start with electroactive polymers. The fundamental effect was demonstrated in 1880 by Wilhelm Conrad Röntgen, and he conducted an experiment with a rubber band which he stretched using weights. And after electrical charging, he observed that the length of this rubber band increases about several %. And when he discharged the rubber, the rubber band shortened again. So this was the first experiment where these effects were observed. Electroactive polymers are electromechanical or electrochemomechanical transducers. We will have a look at the principles later on. And electroactive polymers, like the piezo-ceramics, change their shape when an electric voltage is applied. And they are often also referred to as artificial muscles. We will see that in a short video, maybe why they come up with the name artificial muscles. And since early 1990s, there is a great many of different EAPs which have been developed, but it's still all scope of research and not, I think, industrial ready to be used. And the first video I want to show is about this wiper. Let's see if this works. So this is an actuator made of an electroactive polymer. Here's the actuator, here's a voltage applied, here's a clamp, and when different voltages or electric fields are applied, you can bend this actuator, and we will have a deeper look in it, how it works. So yeah, you can use it for different applications, for example, as a kind of wiper. We can classify the electroactive polymers into electroactive polymers and ionic electroactive polymers. So here's a line missing, but I think you will also get it. Although, so electroactive polymers work due to an electric charge transport and can be electrostrictive, or piezoelectric polymers like the PVDF material, and we can also have dielectric elastomers between two electrodes. And the ionic electroactive polymers, they work with mass transport, so diffusion of ions. And for this we use conductive polymers, ionic polymer metal composites. This is the one we saw in the video, an IPMC. or ionic gels. So now we are looking at the first principle of the electric EAPs, the piezoelectric ones. The piezoelectric effect in polymers has been known since 1924. So yeah, roughly 45 years later than the first experiments by Röntgen. And it has been, well, PVDF is a material which has piezoelectric properties, at least in a certain state, like the piezoceramics, where you need this special lattice structure, so not the cubic lattice, but a rhombohedral, for example. And also PVDF has to be in a certain phase to have piezoelectric properties. We will have a look on that. And it's commercially available under the brand name Cunard since 1961. And in 1969, the Japanese researcher Kawai discovered a strong piezoelectric effect in the material. So it was first commercially available, and then 8 years later, this piezoelectric effect was discovered. PVDF stands for polyvinylidene fluoride. I don't know, that's at least the German spelling. And piezoelectric polymers are like piezoceramics, piezomechanical transducers. And PVDF is the only commercially available piezoelectric polymer, really. And it is used for ultrasonic sensors, also for microphones and for accelerometers. So it's the application is more on the sensing side than on the actuating side. We will see later on why. And PVDF is also the material we used in this multifunctional bond line I had in the first lecture for the crack stopping. So PVDF gives some improvement to the mechanical performance in this adhesive bond line due to its crack stopping features, a toughening of the material. And the original idea was to use this piezoelectric effect to sense also the adhesive bond line. But it didn't work out, so we integrated microstructures into the PVDF to use them as strain gauges, and we will later on see why it didn't work out to use the piezoelectric effect of the PVDFs in the multifunctional bond line. PVDF, I will use the abbreviation for simplicity, is a transparent semi-crystalline thermoplastic fluoropolymer. Thermoplastics consists out of long linear molecules, and when we put energy into them, for example heat, there's a malleable, they become malleable to the point of plasticity and maybe melt. So here we have the chain structure of an amorphous thermoplastic, and a semi-crystalline one is a thermoplastic which has amorphous regions, but in addition also some crystalline regions here, and these crystalline regions we need for the piezoelectric effect. PVDF is, like other thermoplastic materials, extrudable. You can also weld it, for example, by ultrasonic welding. It's thermoformable, it's flame retardant, and also self-extinguishing. And it has also good chemical resistance due to the fluor atom in it, and we can use it over a wide temperature range, but there are also limits we hit in the multifunctional bond line application. PVDF, as mentioned, semi-crystalline, so it consists of polar crystalline and amorphous regions. The amorphous regions are responsible for the mechanical properties, and crystalline regions are responsible for the melting temperature, which is about 178 degrees Celsius. And glass transition temperature is at minus 35 degrees Celsius. And we have 50 to 60% of crystalline regions in the PVDF. So maybe roughly half crystalline and half amorphous. And here you can see in this diagram, here's the temperature. We have here the glass transition temperature, and here the melting temperature. So we have this is the failure strength, or the strength of the material, and this is the failure strain. So very low failure strain and high strength. So the material is really stiff below a glass transition temperature. It's in its operating range between Tg and Tm. It's semi-crystalline, it's hard and tough. So still you can transfer a lot of stresses, but the failure strain goes up. And if you melt it, of course, then you can't transfer any loads any more than the stresses at the failure point go down, and the elasticity goes up, or not the elasticity, but the failure strain. So how does PVDF look like? It's made from the base materials hydrogen fluoride and methyl chloroform, and they are synthesized into chlorodifluormethan and subsequently into vinyl fluoride. So this is the monomer, which looks like this. So 2 carbon atoms, 2 fluor atoms, 2 hydrogen atoms, and then you build a chain out of this to get the polymer. And this is done in high purity water under controlled pressure and temperature using a catalyst. Density is around 1.76 to 1.78 gram per cubic centimeter. Melting point is at 178 degrees. Elastic modulus about 2 gigapascals. And thermal conductivity and thermal expansion coefficient also given here. So why would you say it's a multifunctional or more functional material? Do you have an idea? And why could it be not a multifunctional but only a functional material, if we think about the definition of a multifunctional material? So if we have the piezoelectric properties, we can use it as a functional material, we can activate it through an electric field, but to be a multifunctional material, it should also have load-bearing capabilities. And compared to other structural materials we use, like GFRP, CFRP, aluminium, the elastic modulus is really low, about 2 gigapascals. So here is a square missing, I've seen, so it's Newton per square millimeter. And therefore, I would say PVDF is more functional than a multifunctional material. So now we're coming to the piezoelectric properties, or the piezoelectric material, so phenomenological. PVDF behaves like our lead zirconate, lead titanate piezoceramic. And for the actuator effect, if we apply an external voltage, like we did in the lab to the stack actuator, this leads to a contraction and not to an expansion. So the direction of the fields is reversed. If we apply a voltage, then the material would contract and not expand like the piezoceramic. But most of the time it is used as a sensor. So we use the sensor effect, and then an external load results in an electric charge on the surface of the PVDF, like the piezoceramic. And we only use the D31 and the D32 effects for sensor and actuator effects. So which effects are these? We had other names for it. Transverse, yes. So we not use the longitudinal effect, but the transversal effect in PVDF. And it's mainly used in the form of thin films as a sensor with frequency range between 0.001 hertz to several gigahertz. Sorry, in Germany, I missed it to change it on every slide. We don't have this decimal point, but we have a comma there. So why do we have polarization into PVDF material? We have these fluor atoms here. So we have, again, this monomer made of 2 carbon atoms, 2 hydrogen atoms, 2 fluor atoms. And they draw the electron density from the carbon towards themselves. So therefore, we get an electric dipole in the material. So the dipole exists or forms in the CF bonds here. And so therefore, the piezoelectricity is based on a dipole orientation within the crystalline phase of PVDF. So the polarization is really in the crystalline regions. And we can describe the piezoelectric properties like we did in the last lecture, again with the small signal behavior in a linearized form. The direct piezoelectric effect, again, the electric charge, the piezoelectric constant times the external stress plus permittivity times the electric field, or the inverse effect where we put in an electric field and get a strain out of it. And also the mechanical stresses compliance times the stresses. And we use, again, the same coordinate system. So most of the time the polarization direction is 3 direction. Therefore, we using the D31 and D32 effect, the transversal effects. So the semi-crystalline regions can exist in 5 phases, which differ in parallel and anti-parallel dipoles. But essential for us are 2 phases, the alpha and the beta phase. We have in the alpha phase anti-parallel dipoles, and in the beta phase we have the piezoelectric effect. So here it should read anti-parallel dipoles. It's a small mistake on the slide. This is the alpha phase, and here below it's the beta phase. Here we have 180 degree plus minus 60 degree orientation, and therefore again the effect cancels out, like at the coercive field strengths in the piezo ceramic. We can't use it macroscopically, but in the beta phase we have all the fluor atoms to the same side, and therefore the dipoles also orientated to the same side, and we can use it macroscopically. The piezoelectric beta phase is produced by stretching, and depending on if we do the stretching uniaxial or biaxial, so in plane in both directions, we get anisotropic or isotropic electrical and mechanical properties. So uniaxial stretched D31 is 5 to 10 times higher than D32. So the in-plane directions differ, and if we use biaxial stretching, then the properties are same. So now, how do we come from our solidified polymer out of the melt through the usable piezoelectric material? First, the alpha phase is formed. Again, anti-parallel dipoles, so no macroscopic effect. Then we do the stretching. In the stretching, we get the beta phase in the different crystalline areas. So we have these crystalline areas where the dipoles have the same orientation. And then, again, we have a polarization where we, so to say, turn the semicrystalline areas to globally the same direction, and then we have the macroscopic effect. So this is comparable to the spontaneous polarization in piezo ceramic, and the polarization process is maybe similar to also to the piezo ceramic material. So, and I mentioned that we want to use this effect in our CFRP structure, and the problem was that we have to cure the epoxy of the CFRP material to manufacture the specimen from prepreg material. And by doing so, we reached the melting temperature of the PVDF. So we have lost the polarized beta phase, and we're at the alpha phase. And the integrated material in the adhesive joint in the structure, we were not able to stretch it again, and only polarization didn't work out. So that was the idea to use it, but it didn't work. And so we switched to the microstructure strain gauges, which were then applied to the PVDF. And so we had still the multifunctionality between the crack stopping and the sensing, but not as originally planned due to the piezoelectric effect of the PVDF material. Yeah. Yes, but the application case was for aircraft structures or aerospace structures, and there these CFRP prepreg materials need, depending on the material, 130 to 180 degree as a cure temperature to get their, let's say, stiffness and strength as in the data sheet. So if you would cure it to room temperature, you have lower performance, and also the TG of the material, so the glass transition temperature, rises with higher cure temperature. So you can use it also in a higher temperature range then. So it was a requirement from the material, from the CFRP material. But there are epoxy materials which could cure at room temperature, you're right. Yeah. There's also another effect, the electrostrictive effect, where it's a second order effect. The electrostriction of the material, so like a dielectric material, and it's caused by the asymmetric lattice potential of these distributed domains. And by applying the electric field, oppositely oriented domains would attract each other, and this would lead to a contraction. So this is not caused by the piezoelectric effect, by the electrostrictive effect, but it's far less than the piezoelectric effect. But we can also include it in our equation or in our model for the small signal behavior. So then we have not only the mechanical and the piezoelectric terms in it, but also the electrostrictive effect. M is the coefficient for the electrostrictive effect. I don't have the right name at hand by now in English. I will look it up and give it to you afterwards. So advantages and disadvantages of PVDF. It's suitable for sensors with high resolution in terms of frequency. You can also build actuators from it. It's easy to cut arbitrary geometries from it, for example, with a CNC cutter or laser cutter. From these films, it's very flexible. It has a low stiffness, so you can apply it also to curved surfaces. Low density, especially compared to our piezo ceramic, which has a density of about 7.7 compared to 1.7. Very short response times, therefore it's good as a sensing material. It has again a small energy consumption like the piezo ceramics, and it's cost effective and readily available. You can commercially buy it. But it has a very low Young's modulus of around 2 gigapascals, also low energy density. If we want to have deflections like with the piezo ceramics, you need very high voltages, so up to 30 kilovolts per millimeter compared to around 2 kilovolts per millimeter with the piezo ceramic. So 15 times higher voltage for the actuator operation for the same deflection, which is not large in the piezo ceramic material. So we can only use it as an actuator for low requirements with respect to forces and deflection. And again, it loses its piezoelectric effect like the piezo ceramic when we go up to too high temperatures and melt the material again. going back to the alpha phase, and if we have large field strength, electrical field strength, or mechanical shocks. Yeah, the Young's modulus now over here is written down about 2. It's similar than what I had on the slide before, maybe slightly higher, depending on the manufacturer and on the data sheet. And density of 1.47. It's also a bit different than what I had on the slide here, but it always depends on the data sheet and the manufacturer. You take the numbers out. So if we compare it to PVDF to the piezoceramic, the energy densities are far lower, 0.6 to 20, 0.4 to 5. The free strain is similar, which is achievable, but we need far higher voltages. Blocking stress, 40 megapascals to 4.8, so also a factor of 10. Young's modulus, another number, so we say maybe 2.5 gigapascals for the PVDF and 40 to 64 gigapascals for the Young's modulus of the piezoceramic due to the anisotropic behavior. Coupling factor we introduced in the last lecture is also quite low. It's 0.12 compared to the 647 or 74 of the piezoceramic. The Curie temperature, again we have a Curie temperature where we lose the beta phase, 110 degrees, and the operating temperature is then from -30 to 80 degrees to have a bit of a distance to the Curie temperature. And we need far higher electric fields, and density is therefore lower than in piezoceramic materials. Here's an example of a PVDF actuator. So here are the PVDF actuators, and I also have a video for this. You have to open it up. No, it's not the one. This one. So here you can see it does not loop. Maybe now you can see the actuators working here, made of PVDF. Pushing again, I think a rather small force, but otherwise it could not deform it. So an application example for this would be a PVDF sensor. We have here the PVDF film. It's also transparent. This is how it comes, and then we have the electrodes applied here and here, so on the top and on the bottom side, and the measurement area is here. So this is the sensor active area, which would be here. Here is a coin for a size comparison, and the sensors are very thin, so 25 micrometer. You get the PVDF in thin dimension. You don't need a power supply in this case, and it is adaptable to complex contours, so the thin film you can shape and adapt to your structure as you want. And with this sensor you can transduce pressures from a few kilopascals to up to 40 gigapascals and measure pressure here in this sensor area. Going again to full screen. Yeah. Okay, next class of electroactive polymers. Now the dielectric elastomers, which are also the electric EAPs, but not piezoelectric. they consist out of 20 to 60 micrometer thick elastomer films, for example, silicone or acrylic, and they have planar compliant electrodes. So here is the elastomer film between two electrodes, and the electrodes are also not stiff. They can deform with the elastomer material. The elastomers are dimensionally stable, but we can deform it. And the glass transition temperature lies below room temperature. So we are in this range. So here's the room temperature, here's the melting temperature. Here it is rigid, here's like from the behavior like leather, and we use it in the elastic range, and it would be viscose when we go above the melting temperature. And this is the Young's modulus, so high Young's modulus in the rigid phase and lower modulus here in the elastic regime. They can deform due to tensile or compressive loading by stretching of the entangled molecular change. So elastomers are cross-linked like thermoset materials, but with far less linking points, and therefore they can deform much more than thermoset materials. And it's all elastic, so after unloading they return to their original undeformed shape. And if we now apply an electric field again, so we have the electrodes with the elastomer in between, a field in this direction, we would attract the electrodes against each other and deform the elastomers in between. So we squeeze the elastomer material between the electrodes, and we have a constant volume, so the energy changes with changes in geometry and electrical voltage, but no volume change. And we can again calculate also the stored electric energy like we did before in the last lecture. And also have a video for the elastomer, the dielectric EAP membrane, to get an impression. So it's a look from the top. So we are looking at the electrode from the top. In between is the elastomer, and if we apply a voltage, then the elastomer is squeezed, and therefore it can actuate like this in plane. So again, we have this stored electrical energy, which is 1 divided by 2. Then we have the permittivity in this dielectric material at a constant stress, and we have the area A of the electrode, and L3 is the distance between the electrodes here, L30, the distance between the electrodes, and then we have the voltage applied squared. And we can also could also write it in terms of a change in electric energy, and then it's the change in the voltage. But we'll skip that and go to the next slide. So the second, maybe I go here. So the second term here in the change in the stored electrical energy is corresponds to the converted mechanical energy, and this equals the force acting on the elastomer, and this generates also the stress in the elastomer. So we divide it by the cross or by the area of the electrode, then we get to the stress generated in the elastomer. And we have a behavior like this. So owing to the volume constancy, the in-plane actuation effect can be given by this equation. We have the strain in plane, so strain in 1 and 2 direction is given by this equation. It depends on the compliance and also on the permittivity and the voltage and the distance between the electrodes. So this is the applied field again, and if we plot it, we get this blue line. So just it's not an actual material, but just to get you an impression about how it behaves. We have the applied field here and the strain on this direction, and it doesn't matter in which direction we apply the field. It gives us the in-plane stretching. Yeah. Yeah, it's for reference from another one, but I only had this one, so the blue line is the one we are looking at. Yeah, maybe I have to change it in my slides for the future that I only have one line in it. So by applying a high electric voltage, 2.5 kilovolts, the electrodes attract each other and compress the elastomer, and this causes then expand in the in-plane directions, and we can get planar strains up to 200%, as a rather high stretching, like we saw in the video. But it's limited by low resonance frequency, and also the operating frequencies are quite low, 5 to 100 hertz. But we have a very high energy density. And if we compare it again to our lead zirconate titanate, then we have high active strains, piezoceramic 0.1%, and here up to 250%, depending on the elastomer. But Young's modulus is not 64,000 megapascals or 64 gigapascals, but only 3 megapascals or 0.1 to 1 megapascals. But also the density is around 1, so really a light material. And here we have the same diagram again, like with the blue curve, and now only one line. So the pressure is on the membranes is proportional to the product of the electric constant and the dielectric constant of the membrane and the square of the applied electric field. So it's a squared function, the electric field versus the elongation. So if we, in this range, we need rather a large change in electric field to get a change in elongation, and then since it's squared, here we only need small changes in electric field to get high elongations. Yeah. So yeah, it's nonlinear, so small signal won't work here anymore. Yeah, but we could also assume, let's say, a behavior like this, or maybe like this. So we have to have a regression line in it if we assume small signal behavior. But we won't go into detail for this material in describing it with the equations. I'm not quite sure. I haven't thought about that. No, since you don't have a polarization, right? And therefore you don't have the butterfly curve where the polarization changes. So it don't follow a butterfly curve. Yeah. Okay, what can you do with it? You can use it as a membrane actuator, where you just get the extension in this direction. So you use the in-plane extension. You can build up a bimorph. Have one side an actuator and one side a structural material, and then you can bend it down and up, or you can wind it up and have this kind of actuator. And for this I also have a video. I think it's this one. So here you have different electrodes, and you can move it around a bit like a finger, and I think therefore it's also called artificial muscles. So here you have the membranes with the electrodes wound up. But you can also see it's far from a commercial use. I think it's more like an experiment in research or academia. Okay, with that, we go over to the ionic active electroactive polymers. Here we have a different actuation mechanism. It's now based on mass transport, diffusion of ions through an electrochemical reaction, so oxidation and a reduction, electron release or electron uptake of a metal or conductive polymer. And with this, we produce a change in the volume. We have the electroactive or the ionic active polymer here between the electrodes. And if the ions are evenly distributed, and if we apply an electric fields, the hydrogenated cations or the ions would go up to this electrode, and therefore we have here, let's say, a higher concentration, and the material swells, and here it shrinks. And with this, we can get a bending of the actuator. So we need for this ion conducting polymers, also called ionomers, which are again thermoplastic. We can get them by copolymerization of a nonpolar with a polar monomer, and they have in general these properties, so high toughness and abrasion resistance, high impact and notched impact toughness, transparency, high ionic conductivity. This is what we are needing for our actuators. They are not electrically conductive, and we have a good resistance to stress cracking, so a tough material. We won't go into detail how the conductivity really works out. It's from a dissociation of the molecular bonds, which form electrically charged mobile ions. So we need mobile ions, but we won't go into detail of the chemistry. But an example material is Naphion, which is produced from Teflon, the brand name polytetrafluoroethylene. The monomer looks like this, and it reacts with a sulfonic group, SO3H group. So we have a sulfonation, and this leads to the solid state electrolyte where we have ion conductivity in the material. So we have these monomers again from the Teflon, but now with this sulfonic group. And from this we can also build bending actuators, which consists from two electrodes in gray, and the electrolyte material, the ionomer, in the middle. And the removal of ions during the reduction process leads to a contraction, and the ion concentration on the other side during oxidation leads to an expansion, and so we can move it up and downwards by applying fields in the opposite directions. And we have two variants, one ionic polymer metal composites, IPMC. This is the one we had in the Viper example in the beginning. And an alternative are these conjugated polymers. the ionic polymer metal composites consist of a polymer membrane between two metal electrodes, and the ionomers, which are ion conductive, are required as shown for the actuating effect. And you can build these kind of, how is it called? In German it's a Greifer, so a grabbing device. I don't have a video for this, unfortunately, but it's the same like in the Viper example, but 3 times. We have low drive voltages from 1 to 10 volts. We can only achieve low frequencies, so it's more for a static use case. And we can use the following ionomers, the mentioned naphion or flemion, which is a material from Japan, perfluor carboxylate. Again, like the piezoceramic materials, ionic polymer metal composites also have an hysteresis behavior. So we have here the applied voltage, and here we have a displacement, not U, but W at this time, and this enclosed area is characteristic again for the hysteresis. So again, no small signal behavior in real. So we just, if we use it, then it's a simplification. Mm-hmm. Yeah. Come again? Yeah. Yeah, no, I didn't show it. So I'm not sure if it comes afterwards. So conjugated polymers will come afterwards, but which are also electrical conductive. But I won't go into detail much. Okay. Yeah. So we can have a look at the Viper again. IPMC Viper. So now we know this is made of 2 electrodes made from metal and the ionomer in the middle. And when we change the direction of the voltage, then it turns in the other direction. So it's oxidation and a reduction process happening, and therefore we can have this actuation. Conjugated polymers consist of 2 layers of conducting polymer with an electrolyte in between. So we don't have metal electrodes, but these conjugated polymer electrodes with an electrolyte material. And again, we have an oxidation and a reduction, which leads to swelling or shrinkage of the material, and then the same effect can be used. And this solid state electrolyte we have in between, which is also polymeric, must be kept moist. So if we want to use dry actuators, we have to encapsulate it so that moisture is still in the electrolyte, which limits the application in dry environments. Yeah, I will skip this this slide, but you will get the slides and maybe can read through it if you like. It's a brief introduction how this electrically conductive polymers work. It's through doping, but since I'm not a chemist or not familiar with chemistry that much, I will skip it, and you can read through it afterwards. But we can also from this conjugated polymers, we can also build actuators, and now it's maybe clear why we say artificial muscles to it. So here are actuators from the conjugated polymers. They are transparent, and if we actuate them, we can build hands which has similar to natural movements, just to give you an impression how they are used in research. So going back to full screen again. If we compare ionic electroactive polymers to electric active polymers, we have here for the ionic ones small voltages, 1 to 5 volts, compared to very high voltages up to 2.5, again, not a comma but a point, 2.5 kilovolts. Here we have a limited service life due to degradation effects, and for the electroactive polymers a high service life up to 10 to the power of 7 load cycles. We have not a good efficiency in the ionic EAPs, but a high efficiency. We still have in hysteresis, but a higher efficiency here with electric EAPs. Energy density is high for the ionic ones, but we need an electrolyte, and a liquid electrolyte is enables a better transfer, but we need to encapsulate it, and a solid state one does not need the encapsulation but has limited ion transfer. And for the EAPs, if we have very soft polymers, we have strains up to 200%, and also very high energy densities, but as mentioned, both materials are not yet in practical use. So with this, we close the electroactive polymers and go over to the shape memory polymers, only briefly, but it's also a functional polymeric material. Shape memory polymers are polymers that are shape sensitive to external stimuli, for example, temperature, light, or magnetism. And we have 2 polymer components, which we can use as a switching element between 2 states. They, as mentioned, often consist of 2 components, which are also called copolymer or block polymer. One component is an elastic polymer. It's kind of a spring element, and this is responsible for strength and the permanent shape of the structure. It's semi-crystalline. And then we have a hardening component, which locks the spring component, responsible for the temporary shape of the structure, and this is most of the time amorphous. So 2 types of polymer mixed, one as the elastic polymer and one to harden the component and to lock the shape. And if we have a look at this diagram to get an impression how it works, here's the temperature axis, here's the elongation or strain axis, and here's the stiffness axis. We start here without stiffness with a cool material, and then we heat it up. And as soon as we have heated it up above the transition temperature, we can elongate it and apply stresses and strains. And if we have the shape we want to lock, then we cool it down again and release the external force to deform it. Then we are going down here, so force is removed. And then we have here the, let's say, the new shape of the shape memory polymer. This is the original shape, and if we then heat it up again above the transition temperature, it goes back to its original shape. So this is the mechanism from the original shape to the, which is the memory shape, so to say, to the new shape here. And then if we heat it up again, we can go down here. So this is the way to program a temporary form. And the transition temperature depends on the melting temperature and the glass transition temperature, or is a mixed temperature, and it's defined by the component with the lower Tm melting temperature, or Tg. If we look at this diagram from one side, here's the stress strain diagram, so strain axis and stress axis and strain axis. Then we heat it up, red line, we deform it for the new shape, and then we cool it down, have the new shape saved, so to say, and then we heat it up again above transition temperature, and then we get to epsilon p, and then we could program it again in a temporary form. And there are two characteristic values. We have the shape recovery rate, so it's epsilon m, which is this point. This is the deformation we applied, we want to save, minus the shape we get back when we heat it up, divided by this shape. This is the shape recovery rate, and the free strain rate is the quotient between this point, which is the stored shape, so to say, the temporary shape, and the shape we wanted to get. So this difference is then the free strain rate. Sorry? Yeah, this is the permanent strain we have after the cycle, let's say. Yeah. But it's nearly here, so it's not to scale, let's say, the diagram. And examples of shape memory polymers are thermoplastic polymers with two phases. For example, polystyrene butadiene copolymer. The polystyrene stores the permanent shape. It has a transition temperature of 60 to 90 degrees, and the other component, the butadiene, determines the shape memory effect. And we have the transition temperature between 60 and 90 degrees, so we have to heat it up above 90 degrees, and then it goes back to its original shape. And another example would be covalently cross-linked copolymer, for example, stearyl-acrylat metacrylat, melting point 35 to 50 degrees of the crystalline regions, and this defines then the transition temperature, so far lower transition temperature compared to the first material. And as briefly mentioned, we also have materials which are photosensitive, so you can activate them by light, so they go back to its original shape, and also chemosensitive shape memory polymers, where you can activate it by some chemicals. And yeah, as an example here is from our lab, we have shape memory polymer deformed, so it's more or less, let's say, straight, less straight, but if we then heat it up, it goes back to its original form like a spiral. Shape memory polymers are lightweight. We can cast them, bring them in several different forms. Due to the composition of the different polymers, we can synthesize a wide range of properties and vary these properties with little effort. We have strains up to 1,100% possible, so high strains, and also a good shape recovery of up to 99%. This was the one key parameter we had 2 slides before. But we have low restoring forces and low stiffness. So if you need an actuator with forces, with high forces, then it's not the best material. But if you need large displacements, you could use shape memory polymers. But you have to, you can use it only one time, or you have to think of mechanisms to memorize the shape again, to use it again. Yeah, maybe we also skip that. You can look at this afterwards. It's a comparison of the energy density between PVDF, piezoceramic, and also electroactive polymers with acryl and silicone. So you get an impression of the different energy densities stored in the material we spoke about. And with that, we come to the summary. We have talked about shape memory polymers. Then we have the electroactive polymers like piezoelectric polymers, PVDF films, which are semi-crystalline fluoropolymers, where we use the D31 and D32 effect. We have the dielectric electroactive polymers, the dielectric elastomers, where we use the Maxwell stresses and have very large planar strains at high electric fields. This is the one with the compliant electrode we looked at from the top in the video. Then we have the ionic EAPs with the ionic polymer metal composites and the conjugated polymers, the two types, where we change the volume by ion migration, and then we can build actuators from it, like bending actuators or the hand we saw in the video. And if we look at advantages or disadvantages, PVDF is flexible, light, has a wide frequency range, but low modulus and energy density. The dielectric elastomers have huge strains and also high energy densities, but require also high fields and have low stiffness. So again, large displacements possible, but only low forces. With the ionic electroactive polymers, we have large bending capabilities at low voltages. So if we don't have high voltages, we could go for this one. But they are slow, have a low efficiency, and also a limited lifetime with the electrolyte required, especially when it's in liquid electrolyte and not a solid state. And with this, I'm open for questions. Okay. If we don't have any questions yet, feel free to reach me afterwards. And I think we switch back to our timetable. Back to our timetable. So now we will have our tea break. Our tea break. And after tea break at 4:15 p.m. 4 p.m. So 3:30 to 4 is now tea break. And at 4 p.m. You start with Hendrik in the second lab, and we'll do the butterfly hysteresis like seen yesterday in the lecture. Anything to say regarding the lab? I think we will go not with 4 groups, but again with these 2 groups. I think it worked well in the before lunch, and otherwise I think it takes too much time if we want to have 4 groups. So like the grouping like before, 2 larger groups. Okay. Then thank you very much and see you.